Hey, thank you. Thank you for the introduction and for the invitation. So actually, it's a great pleasure to be here. I have denied a lot of invited talks lately because I have a baby, but I couldn't deny CITA because I wanted to come to Canada before going back to Europe. So I came with my husband and my little baby. So if you see someone with a little baby, that's my husband around. They are seeing Canada for the first time, so they are also very happy. So today I'm going to talk about my research, which is focused on the very first steps of planet formation, so from cosmic dust to planetesimals. And you will see during my talk that I work on models and observations. So this is a parallel research that you will see also in this presentation. The global idea of my work is, of course, to understand how planets form. And we know that they form in protoplanetary disks that are a product of the star formation process. And the initial composition of these objects is mainly a gas. So 99% of the material is gas, and only 1% of the material is dust. And this dust is initially as the interstellar medium. So we expect these grains to be submicron or micron-sized particles that collide and form terrestrial planets or the core of giant planets. The lifetime of protoplanetary disk is around 3 to 10 million years, and after that, all the gas is accreted onto the star. And therefore, we expect that at least giant planets are formed before all the gas is gone. And a more specific question that I want to answer with my research is how the initial conditions and the physical processes that rule the evolution of these objects can affect the final output. And when I say the final output, is the properties of exoplanets. So we know from the last decades that there is a large diversity of exoplanets. And this is just an example of the multiple planet systems that we observed with Kepler in comparison with the solar system, that we see in dashed lines the orbits of the solar system compared with the other ones. In this movie, the colors represent the equilibrium temperature of the planets, the size of the points, trying to show the size of the planets too, but it's not in a scale. And this is just to show that we have a large diversity, but in particular, our solar system seems to be unique or special so far. And the whole process from cosmic dust to planets is a long journey that covers around 40 orders of magnitude in mass growth, and it's mainly divided in two. So we have the evolution from micron-sized particles to what we call planetesimals, or kilometer-sized objects. And all these are regulated by the interaction with the gas. So here is very important where in the protoplanetary disk we are and how much gas there is around. Then the second part is from planetesimals to planets, or the core of giant planets. And the growth is regulated by the gravitational interaction between objects. So I'm mainly interested in the very first steps of planet formation, also because we have observational access to this phase. From there to what we call pebbles, millimeter, centimeter-sized objects, to planetesimals, is very difficult to observe. And therefore, we rely on connecting these very first steps of planet formation with exoplanets to understand what happened in between. And from observations, we can actually reconstruct the distribution from micron-sized particles, or even smaller, to pebbles. For example, to observe the very small grains that we expect to be in the surface layers of the disk, we observe these objects at optical and near-infrared scattered light. And these are beautiful observations that we have obtained with a sphere at the VLT of different protoplanetary disks, where you see also different kind of structures, such as rings, gaps, spiral arms, shadows. And also even these spiral arms seems to be very different from each other. So I'm going to talk a little bit about these structures also in my presentation. On the other hand, if we want to observe the pebbles that are in the midplane of the disk, we observe these objects at millimeter wavelength. And we have seen beautiful observations recently from ALMA, where we also see a large diversity of structures, but the most common here is actually gaps and rings. And by observing these disks at different wavelengths, we can, as I said before, reconstruct what is the distribution of the small and large grains. And this is very important because the dust is a tracer of the physical processes that regulate the evolution of the gas, which actually, in principle, is very difficult to observe directly. So we can learn about what is regulating the gas evolution, which is the main component of these objects. And with that motivation in mind, let me bring the outline of my talk. So I'm going to present you what are the kind of models that I work, and these models include the growth and the dynamics of particles in disks. Then I'm going to tell you what we have learned when we compare these models with observations of protoplanetary disks. And then I'm going to show you some current investigation and future perspectives in this field. So the dust evolution model. So when I talk about dust evolution, I'm talking about the transport and the collisions of the particles. And these two physical mechanisms are very important to model together. I will show you why in the coming slides. Here I'm just giving you examples of what are the physical mechanisms that can move particles in the disk. And by these mechanisms, we can collide particles and change the particle size. So let's go first to the transport of the grains. So we can move particles in the disk due to Brownian motion. This is only important for very small particles, so submicron sized particles. And it depends on the grain size and the temperature of the disk mainly. We can also move particles due to settling. So particles in the surface of the disk, mainly micron-sized particles, can settle to the midplane, and once they are settling, they can also collide and grow, and the bigger they are, the faster they settle to the midplane. So this also depends on the grain size. On the other hand, we expect this disk to be turbulent, and therefore particles can couple and decouple continuously from these turbulent eddies. And these mixing timescales depend on a diffusion parameter that usually depends also on the grain size. And finally, we also have the radial drift of the grains. I'm going to explain this in the coming slides, but this also strongly depends on the particle size. And this is to say that all of them depend on the grain size, and therefore we need to model the collision of the particles with the transport of the grains to model correctly dust evolution in disks. So when two particles collide in the disk, basically we can have different kind of outputs. And this is what I'm showing you here. This is a cartoon of what can happen. So we have two grains before collision. When they collide, they can stick, they can bounce, one particle can transfer mass to the other. We can have erosion, or we can have fragmentation. And basically, the potential output depends on the cross-section, the collision, and the relative velocity between the particles. And you can calculate this if, for example, you take into account all the transport mechanisms that I just mentioned, and you calculate what are the velocities, and you set a threshold for the velocities before the particles fragment or erode. And this change at different, yes?
In these scales, the dust particles would be circular, and some of them would have irregular shape?
Well, it is an interesting question. We assume they are spherical for this particular calculation, but they can grow very fluffy also, and I'm going to show you actually some simulations of that. In this case, yeah, we consider that it's spherical, and in this plot you are seeing what is the potential output if they collide at 3 astronomical units from the star. So in both axes, we have grain size. If the collision happens with very small particles, there is perfect sticking. Then between micron to centimeter-sized particles, you have sticking or bouncing. But overall, you have growth. So this is why you have this area in green. Then if you have only collision between between centimeter-sized particles, then what happens is that you have only bouncing. And this is why it's in yellow, because this is a barrier for planet formation. But if you overcome this bouncer barrier, then you have growth basically because of mass transfer, where one of the small grains transfer mass to the big ones. And when particles grow very big, like meter size, you expect to then have fragmentation and erosion of the particles. But how we know actually what are the fragmentation velocities of the grains? This we know thanks to numerical calculations and also laboratory experiments. So I'm showing you here an example of those numerical experiments. So on one hand, in this side, you will see the collision of two aggregates that actually, in this case, they are very fluffy initially. And they are composed by ice. So what we call here a monomer is the minimum grain size that is assumed that is part of these big monomers of each of these points here, basically. And the collision happens here at 8 meters per second. And you would see is that the collision ends in a very perfect sticking collision. And the final object is much more compact than the initial one. If we change the composition and now we have silicates and reduce the velocity, actually what would happen is that some of the monomers collide and stick, but many of them are also lost. So this is a combination of stickiness, but also part of them are loose.
So in the first case, what is the extra energy go?
Pardon?
What is the extra energy of the collision? It seems like they were moving at first, now nothing's moving. So
No, well, then basically the simulation is over after you have the collision between the grains. It's only to see what is the final grain size, and that's it. You are not modeling for instance, the movement of this particle in the disk or anything. And I'm going to talk this also later, but basically the forces that make the particles to stick are the van der Waals forces. So this depends on what is the composition of the grains. And basically from these experiments, numerical experiments and laboratory experiments, we know that water ice is very sticky and that the fragmentation velocities are 1 order of magnitude higher than silicates. And in a protoplanetary disk, we actually expect that most of the grains will have at least from 1 AU outwards, at least a mantle of ice. So we expect fragmentation velocities of the order of 10 meters per second in most of the disk. And I want to go back to the radial drift problem because this is kind of what motivates all the research that I have been done and a lot of the results that I'm going to present you. So this movement of the grains comes from the fact that the gas move sub-Keplerian while the dust move exactly Keplerian. And this is because if you take a parcel of gas and you calculate what are the forces that are in that parcel of gas, you need to take into account the gravitational force, the centrifugal force, and the pressure support. And because of this term, the velocity of the gas is not exactly Keplerian, but it has an additional term here that depends on the pressure gradient. And the pressure in a disk is proportional to the density and the temperature, and both are expected to decrease outwards, and therefore this is a negative term, and the gas moves sub-Keplerian. So if you put typical numbers here, it's something like 99% of the Keplerian velocity. So it's a very small difference, but the particles feel this difference because they don't feel the pressure support, and they move Keplerian. So they tend to lose angular momentum and move inwards. This radial velocity depends on the grain size. So this is what you are seeing here, the effect of the radial drift. So we have in the y-axis the dust radial velocity as a function of grain size, calculated at 3 AU distance from the star. Small particles that are well coupled to the gas move with the gas with very low velocities. This is not exactly 0, but it's very close to. And then when they start to increase in size, the radial drift starts to gain more importance, and the velocities that they can reach in this case are very high, like around 4,000 centimeters per second. They are negative because they are inwards. So imagine that you have around 1 meter size objects colliding with these velocities. They will probably fragment. And if they don't collide, they anyway go towards the star in less than 1,000 years. That is a time scale that is much shorter than the times that they need to grow to planetesimals. So this is known as the radial drift barrier in protoplanetary disks. And this is here shown in these dust evolution models where we consider the growth and the transportation of the particles in the disk. So you will see in colors the dust density distribution as a function of particle size in the y-axis and distance from the star. Initially, we assume all the grains to be as the interstellar median, so micron-sized particles. The white line here represents the shape of the gas surface density, so we have a smooth disk, and therefore we expect particles to move inwards because the regions of high pressure in the inner disk. And you see that in the inner disk we have plenty of collisions, very effective because the densities are really high, grain growth happens very fast. in comparison to the outer disk, where the densities are lower and growth happens in longer time scales. But once particles reach certain sizes, what you see is that all the grains are going to be lost towards the star. And at million-year time scales, we don't keep any planetesimals in the inner disk, or we don't keep any pebbles in the outer disks. And we know somehow that these, of course, have to be overcome. And the most common idea is that we have a pressure bump in the disk. And this was an idea that it was introduced already in the 70s. This is a figure from the paper by Whipple in 1972, where he proposed that if we have a pressure bump, we will have an accumulation of particles in the pressure bump. And that's basically because the velocity of the gas in the region where the pressure gradient is positive will be super Keplerian, so particles will move outwards. Here the particles will move inwards. In the pressure maximum, the drift disappears. And well, as a result, you have a natural accumulation of grains where they can also grow to planetesimals because you reduce the fragmentation velocities. So the key question here is what can create these structures in the disk? And that's what we are trying to do nowadays, and how we can distinguish actually observationally. So one idea is that we have already a planet embedded in the disk that is opening a gap in the gas surface density, and as a result, we have a particle trap. Nevertheless, in this case, we will have a chicken and egg problem because we will need a planet to create the first planetesimal. So it's not really a solution, but it's a possibility to trap particles. The other option is that we have a region of low ionization in the disk, and at the edges of this low ionization region called dead zone, we can have accumulation of gas. And in these locations, we can trap particles. And I'm going to show you examples of this trapping mechanism. We can also have bumps from magnetic fields in the disk, and these are simulations, 3D MHD simulations from Ana Uribe in 2011, where they see these regions of high pressure that they call zonal flows. And these pressure bumps are usually of 20 to 30% of amplitude in these simulations. The other possibility is that the disk starts to be very massive and cold enough to be gravitationally unstable, and when they are gravitationally unstable, they can fragment and form spiral arms, and these spiral arms are regions also of high pressure, and they can trap particles. And this is just as an example of the accumulation of centimeter-sized particles in these kind of spiral arms. And finally, we can also have vortices that can be formed by different mechanisms. In this case, I'm showing you an example where we have the Rossby wave instability due to a planet, in this case, and at the outer edge of this gap, we see vortices forming. In the beginning, many vortices form, like 3 or 4, and then eventually they merge to a large scale vortex. And these are also regions of high pressure where we can accumulate particles. So let me summarize what is the first part of my talk. So we started in this disk with micron-sized particles that collide and grow, but also when they collide, they can fragment. And this is very important, actually, because fragmentation replenishes continuously the disk in small grains that we actually observe. Once particles grow to certain sizes, we expect them to drift inwards very fast unless we have regions of high pressure where they can accumulate and form pebbles or planetesimals, and due to the accretion of pebbles or planetesimals, we can actually create terrestrial planets or giant planets. If actually we form a giant planet, then we will create a second generation of a particle trap that can help for the formation of a second planet. Okay, so I'm going to move to the second.
The whole business of opening the gap, if you model that in not anti-symmetric, but multi-dimensional, like 2D or 3D, people are finding that gas is able to cross the gap and make it inside. So if that's the case, and you drag the notion that the pressure barrier is true in an axisymmetric sense, but actually if you look at the multi-dimensional problem, it seems to me you'll be able to bring the small stuff through the gas, crossing the gas.
Yes, so I'm going to talk a little bit about that. You can have flow of gas through the gap, And with that, you can bring small grains. You can bring small grains from the outer disk to the inner disk, and those small grains then in the inner disk can grow very efficiently. That if you don't have anything that traps those grains, then they will drift. So it will look like an empty cavity. The filtering effect depends strongly on the grain size. So large grains, like millimeter, centimeter size particles, they don't have a way to go through the gap, actually. So they will remain in the outer part of the disk. This strongly depends on the planet mass and the disk viscosity, because the higher the viscosity, the higher is the turbulence that the particles feel, and how they can diffuse, and therefore if they can or not flow through the gap. Yeah. Okay, so let me move to the second part. So what happened when we compare actually the models of dust evolution that include the drift with observations? We cannot observe directly the grain size, but we can infer it from millimeter observations. And that is because the opacity of the grains at millimeter wavelength depends strongly on the particle size. So this is the opacity as a function of wavelength. You see that at millimeter emission is usually a power law, and that it becomes flatter for larger grains. So if we write this as a power law with a beta index, when beta is lower than 1, we can conclude that grains have grown to millimeter sizes. We don't observe the opacity directly, but in the optically thin regime, the millimeter flux is proportional to the opacity, and as a consequence, the millimeter emission can be written also as a power law that is directly connected with this beta index. So if we have multi-wavelengths observations that we need only 2 wavelengths, we can obtain this alpha and conclude something out, the grain size in protoplanetary disks.
The colors here, the opacity.
Pardon?
The colors there.
Yes, so the colors is changing the grain size. So I don't have in the top of my mind what exactly is for each color, but it's going from assuming the maximum grain size to be micron to very large, I would say, meter size.
So we could expect particles to interact with comparable wavelengths. So you see they diminish in the vertical axis, but you would expect things to shift in the horizontal direction also.
Well, I guess in this case, like you expect this to decrease faster here, you mean? I think it's decreasing, but it's no. I mean, if we look at, well, no, something like millimeter, yeah. Well, I don't know exactly what you mean with moving horizontal. Like you expect this to decrease like this?
I expect to have an absorption, diffusion absorption, where you have a wavelength of comparable size to the size of the grain.
That's true, but here we will have something. Maybe I was exaggerating that will mean meter size, but probably centimeter size for this one and these micron size particles.
Yeah. There's a difference between which size particles dominate the capacity and which size particles dominate the mass, because the capacity is a function of size.
Yeah, but is this for a single population?
No, this is assuming a power law. And what is changing here is the maximum grain size in the power law.
Yes, okay.
Yes, so usually it's assumed minus 3.5 power law. Yes. And in this plot, what we see is a collection of data for different protoplanetary disks in 2 star-forming regions and around different types of stars. And alpha is calculated between 1 and 3 millimeter. And you see that for all of them, we have alpha lower than 3, meaning that we have grain growth in this disk, also independent on the disk dust mass. So we knew that this from observations, but when we compare with the models that include the radial drift, we could not reproduce this because basically all the dust is gone, so alpha tends to increase and the flux also tends to decrease.
So this is assuming optically thick.
Yes.
So if it's just to remind you, if it's optically thick and there's some kind of temperature profile, what do you expect alpha to be?
Yes. So then the relation is not so direct, and Yes.
And you need a temperature profile.
Yes, you need that. Yeah. So you can assume that. Yeah. Basically, oh, sorry. If you include a temperature profile and well, alpha also will decrease for grain size, but no exactly will be that if it's lower than 3 means that we have millimeter size particles. It will have.
Because I'm curious, is the observation has ruled out up to the thick case?
I think we should be careful with the optically thick cases to the interpretation of alpha. Most of them, and recent ALMA observations show that most of the emission is partially optically, it's mostly optically thin, let's say. So that tau is close to 0.5. Yeah, we know now from ALMA observations that many of these observations are optically thin. So the D-sharp sample that actually target the brightest disk, when they calculate tau, is something like 0.6, 0.5. So still in that regime, the alpha interpretation in terms of grain growth is valid, still remains valid.
Well, we should talk about it, because I'm actually confused. I thought it's pointing out everything's optically thick now.
No, actually, I'm surprised because I was also expecting that the sharp sample, as I said, the brightest disk, the most massive disk, they seem to be, at least in the rings, they are optically thin. HL tau is an exception, I think, in that case. HL tau is the inside the rings is optically thick. Yeah.
And the other one we know the rings are very massive.
Yeah.
This is very massive.
Yeah. Yeah. Okay, so we wanted to actually have like a better agreement with those observations back in 2012, but including pressure bumps in the disk and just simply to know what kind of pressure amplitude we need to trap the grains and explain those observations. So we perturb the density of the disk with a simple assumption. We keep the wavelength of that perturbation as 1 scale high, and we investigate how this amplitude will change the previous picture. So basically, by just doing some analytical calculations, we can calculate what is the minimum amplitude to have this condition, and we found that it has to be 10%.
That depends on L. So
Yes, so in this case, we fix it to 1 scale high. Yeah. Yes, of the disk. We also, in the paper, we also explore what happens if we have something like 3 times this scale high. But in this case that I'm presenting you here is 1 this scale high. And what you see here is that we started the dust evolution models with that amplitude, and then we increase it. You see, well, in the case of no perturbation, the dust that we have in the outer disk in comparison with the initial dust as a function of time is decreasing very efficiently. Also in the case that we have amplitude of 10%. And we were kind of surprised with this result because we were expecting particle trapping because we were having this already fulfilled in our calculations. But what happens in this case is that we also have
So is this the dust just in the pressure trap or the dust across the entire disk?
So this is basically in the entire disk. So if you plot this, will be like wiggles around the entire disk that increase the wavelength will increase with radius. Yeah, yeah. So it's in the entire disk case. But in here we were only calculating the dust in the outer disk because mainly, basically, this information that we have here is from the outer disk. So in this case of 10% of amplitude, what you see is that even though we expect trapping, what is making the grains to be out of these pressure traps is the diffusion. So in this case, actually, the diffusion of the grains wins over the potential trapping. So the particles, even though we expect to be trapped, they are diffused from the pressure traps because the pressure bump doesn't have enough amplitude.
Corresponds to the estimated viscosity?
Yes. So in this case, basically, we have alpha 10 to the minus 3, and we assume the Schmidt number to be 1. So yes. If we change for alpha 10 to the minus 4, this picture will change. So for even 10% of amplitude, we may have more retention of particles. This is also something we explore in the paper. And what you see here is that if we increase to 30% of amplitude, we have efficient trapping. Some of the grains are lost toward the star, but most of them are in the outer disk, even at million-year timescales. And having something like 50 to 70% of amplitude is like completely reducing the radial drift. And this is how the dust density distribution at 1 million years of evolution look like in those cases, the no pressure bumps, the pressure bumps of 10% of amplitude. So you actually here see this effect of the, well, basically what is the assumption for us in the gas surface density, because it's the white line here. The case of 30% of amplitude, where you see very efficient trapping. And these are assuming the global pressure bumps from MHD simulation. So basically assuming that they live for a very long time and that they are static for million-year times. So we see that those, in principle, can trap also the grains. When we take this dust density distribution and combine it with radiative transfer calculations to calculate the fluxes and the spectral indices, then for those cases, we had a better agreement with those observations. So in this all data from even 10 years ago were already telling us that we need something to retain the particles in the disks.
These simulations have multiple pressure bumps across the disk.
So you can see actually the profile of the gas surface density in the white line.
Okay.
So it's several locations where we have variations of the pressure. Only some of them in the gas move super Keplerian. So, so yes, when we took these dust density distributions and imagine how we'll look at this if we will have high angular resolution and sensitivity, this was what we predicted, that we will have multiple rings and gaps around the young star. And we know now that this is what we are observing at different wavelengths with ALMA, but also with a sphere that is tracing the small grains in the disks. And as I mentioned before at the beginning of the talk, that ALMA is actually now resolving these rings and gaps, which seems to be the more common type of structures here. So although I love these images, it was not surprising because theory was telling us that we need this kind of structures in the disk to explain the previous observations.
Let's go back. That one right there, 205, doesn't seem to have
Yeah, this is really, yes, this is really intriguing to me because it's very large. It's a very large disk, smooth. So something is strange there. I don't know what is going on. It's a binary though. So I don't know if that may affect something. Yeah, it's not all of them, it's true. Something interesting from this is that we found back in a paper in 2013 that the radial drift around very low mass stars, so brown dwarf, is a much more difficult problem in planet formation. This is because if you calculate the drift time scales for a disk in around a brown dwarf compared to a Tauri disk, you see that the velocities can be twice or even larger. And this is basically because the radial drift depends on the difference between the gas velocity and the Keplerian velocity. And this difference is proportional to the 1 over the root square of the stellar mass. So if you have a low mass stars, you have a higher radial drift. And we have actually evidence of millimeter grains in brown dwarf disks. So in coming back to that plot, we have included here data from brown dwarf disks that also show low spectral indices. So this disk probably also have rings and gaps. And if we will ever able to resolve them, they should be like more predominant than the T-Tauri disk or the Herbig disks. So this is something to be investigated in the future with observations. So I want to move to the third part of the talk. So basically, so far, I told you we need pressure pumps, that we have different origins, but I have not shown you the difference between different kind of origin of this structure. So for that, I'm going to talk about a transition disk. This disk, the main characteristic are there are objects with dust-depleted inner cavity. So these are observations obtained with ALMA. All of these disks are heat transitional disks. In some of them, you see clearly the cavity and a ring-like structure around. In some of them, it's not so clear, but all of these cavities are resolved in the visibility plane. So, and the two more competitive ideas to create these cavities is that we have a dead zone or a planet embedded in the disk. I'm not talking here about photoevaporation because photoevaporation predicts small cavities and low accretion rates, and for all of these, actually, the accretion rates are high, between 10 to the minus 9, 10 to the minus 8 solar masses per year. So this already rules out photoevaporation. Well, yes. You mean for the models? What? Yes. So yes, this is measured with X shooter. So usually in the UV range. Yes.
What are the physical size of these new cavities? Like 10 AU?
Okay. See, yes. Here is we have. They are large. The ones resolved here between 30 to 80 AU. Yeah. Here, for example, this one that is not resolved, but is in the visibility resolved, is 13 AU. So, yeah, but most of them are. This one is 60 AU. It's 50 AU. It's the ones I know by heart. Okay, so we actually model the evolution of the dust in the case of a dead zone that is extended up to 20 AU versus a planet, a very massive planet embedded at 20 AU. So these are the snapshots of the simulations at 1 million years of evolution. So what happened at the outer edge of a dead zone is that because accretion depends on the viscosity, it's directly proportional to viscosity. So in the dead region, the accretion rate is low, in the active region is high, and as a result, you have an accumulation of gas. So that's what you see here in the white line. It's an accumulation of gas at the outer edge of the dead zone. And that bump can create a trapping, and actually it's very efficient. It grows up to the larger size that we have in our simulation. If we calculate the amount of dust that we have here, it's something of like 100 air masses. So in this case, actually, we can have very efficient trapping, and it's so efficient that we expect the streaming stability to be effective and to create, for example, the first core of a giant planet. On the other hand, well, this is kind of the distribution that we have if we have a 9 Jupiter mass planet at 20 AU. The main result here is that the gap in the gas that you see in the white line extends, the outer edge extends around 25, 30 AU, and the small grains will follow that. So if we see a cavity in small grains, it will be as extended as that. But the millimeter grains particles will be accumulated much farther out, in this case around 45, 48 AU. While in the case of a dead zone, actually, we have cavities that it will look similar at a short and long wavelength. And when we combine this with the radial transfer and instrumental simulations, this is what we predict, that we will have cavities in the two cases. But the cavity in the case of a dead zone will look of similar size that in scattered light that a millimeter wavelength. While in the case of the planet, this is where the planet is located in this simulation, the cavity will increase with wavelength. So in principle, we can distinguish. And we recently collect a sample of 22 transitional disks that have been observed with the scattered light and ALMA, mainly a sphere for the scattered light. And you see here the scattered light cavity and the millimeter cavity. The green line is the relation where both are the same. In all cases, the scattered light is similar or smaller than the millimeter. There are some cases where it's very close to the relation, and it could be due to dead zones, according to these predictions that we have. But around 2/3 of the sample, we have that the segregation is large, so it has to be explained by a massive planet. and in 1/3 of the sample is the difference is so big that the planet has to be more like a brown dwarf. So in most of these disks, there are campaigns nowadays to detect these planets.
Sorry, so lower limits is already. My limits are lower limits. Sorry.
Yeah, so this is basically the lower limits is because it's smaller than the chronograph.
You
That
don't
way.
see the cavity instead of.
We don't see it, but we have a chronograph that it could be smaller than that. Right?
So, can the brown dwarf allow satellite? Why would the brown dwarf because of already?
So in that case, that means that we have like for example, these ones we will have a cavity of around 60 AU, but in millimeter wavelength, but something like 15 AU or 10 AU in a scatter light, which means you have a very big difference. So basically here, this difference between the scatter light cavity and the millimeter cavity depends strongly on the planet mass. So the larger the planet, the biggest is this difference.
Are there enough brown dwarfs to do that?
You're putting brown dwarf at a few AU.
Mm-hmm. Yeah.
There's no brown dwarf.
That's what I'm asking, yeah. Are there any brown dwarfs in those regions?
You mean if we have constraints from observations? I think there are limits for many of them.
There's the brown dwarf desert, right? Like, I mean, it's really rare to find brown dwarfs a few AU from the first star.
Well, this is out of 50 or something, but, or no, yeah. Were you inside of 10? I guess.
It will need to be inside this, like
Inside
10 AU, yes. Yeah.
I'd be worried that there aren't enough brown dwarfs. Right?
Yeah. Or it's a binary system and we haven't been able to detect the companion. Yeah.
I guess I don't understand the physics. If it's a binary or brown dwarf, so the perturbation is very strong. Doesn't it open a very sharp gas gap?
Yes.
Why would it get such a big extension of no place?
But that depends also on the location. So imagine this example, if we move this to, I don't know, 1 AU. So the small grains that are coupled to the gas will have the cavity will be as extended as where the edge of the gap is.
I understand, but why would the gap shape be like this in the case of massive conservative? I mean, I expect it to be cut out very sharp.
Okay, you mean like why is that?
Yeah,
This?
why is
Well, in these cases, we explored up to 15 Jupiter mass. So we didn't explore the brown dwarf so much. What happened from 5 to 15 Jupiter mass was that the disk was becoming eccentric. The gap in itself was becoming eccentric. So that makes that this shape of the gap is not so sharp anymore, but it's mostly increased with radius.
Did you see the satellite?
No, we don't see it. That the gap itself is eccentric, no. Yeah. But yeah, that's true. We may have some evidence from some eccentric rings at millimeter wavelength. Yeah. Okay, and here I'm showing you an example of that kind of segregation from observations. So this is a disk known as J160421. It's located in upper Sco, so it's around 10 million years old. What you see here in color is the observations from a sphere in 2015. You see a ring-like structure that is peaking at 60 AU from the star. We also detect a dip of emission that I'm gonna talk about a little bit about it later. I overlap an old ALMA observation that you see in contours here, and it's peaking around 80 AU. So you see more like the kind of segregation that we have in this radial profile, where we have the polarized surface brightness azimuthally average from the sphere data. So this is at 0.6 microns. You see the ring peaking around 60 AU, and the ALMA peaks around 80 AU. So according to these models, to create this 20 AU difference, we will need a planet around 5 to 10 Jupiter mass between 20 to 40 astronomical units. About the dip, something that is interesting is that the dip was before observed with high Chao, 3 years before our observations. So our observations detect the dip around 48 degrees from north to east, but the high Chao observations show the dip around 85 degrees. So that means that if the dip is the same, the rotation, and if it's clockwise, the rotation happens at 12 degrees per year, which is much faster than the Keplerian rotation at 60 AU. So that this variability has to come from the inner disk. So for this reason, we actually wanted to reobserve this disk in time scales of years, months, weeks, and days. And this is what we did with the sphere. I'm gonna just tease you with the observations because I don't have time to go to explanations for this at the moment. But this is what we have. We have the high Chao data, then the sphere data, and then what we obtained in 2016 and several in 2017. So what you are seeing here is that we now have 2 shadows, and that the 2 shadows actually change in location slightly, but also in shape, in morphology.
Is this due to an inclined inner disk?
We believe that there is an inclined inner disk with respect to the outer disk. If we calculate analytically what should be the inclination to create these shadows, we obtain something like 70 to 90 degrees. So it's a highly inclined inner disk.
If you have another inclined disk, won't you see this in polarization, or you just have the polarization?
How it will...
You have reflections right from 2 different oblique angles.
But that's basically what is creating the shadows itself, that you are blocking the light of the star, right, in 2 sides. So you shadow the outer disk.
Won't you explain also reflection from the disk, from the occultist, where the disk is producing the shadows? So, right, if you have if you have a surface, then you reflect from it, then you get the polarization. If you have 2 surfaces, then they lessen the polarization, right? Because now you're in 2 different polarizations.
Yeah, but if it's from the same surface, it's just a different angle, right? It's
So
still going to be. Well, yeah, but when you get repolarized, it's going to still eliminate the same function. It's going to modify it, right? But not messing up.
Oh, we should let her continue.
Yeah, sorry.
Yeah, what I want to say here also is that you see that even within days, these shadows are changing. So we are very puzzled of what is creating this variability.
So but just to make sure we understand the observation, so you see these variations in the brightness. Do you see variations in polarization or not?
We see variations in polarization too, yes.
And they're correlated?
Yes, yes.
And what's the size of that? Just the
So this is at 60 AU, the ring. Something interesting is this is also a deeper star. And from ALMA, actually, the inclination of the outer disk is almost face-on, so it's an inclination of 6 degrees. And having a very inclined inner disk explains why it could be a deeper, or why it's a deeper.
So the idea is that the inner disk is precessing, is that the notion of why it's changing?
Probably, but it has to be it has a very sharp precession, and it has to be somehow asymmetric because one of the shadows changed more dramatically than the other. So,
You're talking about like 5 years.
yeah.
What's the shortest time scale? Is it day, you said?
Yeah, it's a day. So it's sorry that the movie is a bit fast, but from 2016, then we have several observations. So August 13, then it's 1 day, for instance, then 3 days.
Our speaker has already given us examples of maps of the emission in the outer parts of the disk that are very non-axis symmetric. If you had such a structure in the inner disk,
Yeah, you can have like a vortex.
Daytime scales.
on the optical.
Yeah, but on a daytime scales, yeah.
Yeah. Near the sublimation.
Yes.
Sublimation radius.
You guys just done a simple estimate of the torque exerted on the potential inner ring by the government? How fast that recession period would be?
No, we haven't done this calculation. No.
It's going to be new times longer than
That's
some
the dynamic.
period.
Yeah.
Okay.
So I have a question. This is they're all sphere rings. Is it?
These are all.
So in all, can you see the gas?
Yes, there is 12 CO and 13 CO and C18 CO. There is a cavity.
There's a cavity.
There is a cavity. It's smaller than this one actually.
Why would that be? Because the time scale, certain time scale is longer, right, than the
No, no. I mean, we don't see the variability in ALMA or anything like that. No, it's not. It's smaller. The gap in the gas is smaller than this. It's around half of the size.
Not necessarily features.
The shadows, we don't know. We don't see them. We don't see them in ALMA.
Shouldn't be able to see it. Certain time scales are not.
What is? Yeah, we don't see them in ALMA. We only see like in the gas a cavity, and there is some hints also of no Keplerian velocity in the inner disk. Yeah. Okay, so this is kind of a summary of what I just explained about the potential origin of transitional disks. So it could be invited planets or dead zones, and we expect in both cavities at the millimeter and micron-sized particles, but the main difference here is that the segregation that we expect in each case is different. Another way to distinguish between this...
Just back up for 1 second. So you say you expect a different cavity size in case that it was a dead zone. So are you so bold to say that you're seeing embedded planets rather than dead zones?
In most of them, yes. So the plot I showed before, that so far, around 2/3 of the population seems to be more in agreement with the planet. So another way to distinguish is by observing even a longer wavelength, so comparing submillimeter wavelengths with millimeter and centimeter wavelengths. So basically, this is the predictions for the planet model versus the dead zone model that I showed you before. It's exactly the same model, but now I'm showing you the dust density distribution for different type of grains. So you see in the case of the planet, we have the accumulation of grains narrower for larger particles. This is basically from the trapping mechanisms, more effective for larger particles. In the case of the dead zone, there is an effect also that the viscosity change inside the dead zone, and this changes the maximum grain size the particles can reach. So inside the dead zone, they can actually grow to larger particles, and as a consequence of that, we would expect a shift of the emission for larger grains. And this is the synthetic intensity profile for these models when we convolve with a Gaussian being typical of ALMA. And we would be able to resolve this kind of shift a longer wavelength. So we have few transitional disks that have been observed at these different wavelengths. So this is an example of SR24S observed in band 9, band 6, band 3. And what we notice in this case is that all of the rings peaks a similar location. So we are here saying that it's likely to be also a planet more than a dead zone. If I have 10 minutes of time, I want to talk about Iceland.
Conclusion that there has to be another process that we don't understand yet. That is allowing you to stop the drift in the first 1,000 years, so that at 1 million years we do have a planet that actually leads to a
yes. Although what I was also explaining about the dead zone, for instance, is that you accumulate so much in that location, you expect a giant planet to form. So you could have had before, early in the disk, a dead zone creating the giant planet. Yeah. And the formation of the giant planet actually will change the whole ionization of the disk, because you change the density and. I see that I'm super short on time, so couple of minutes. So yeah, then I will probably skip to, because this is more than a couple of minutes. I will skip to the conclusions. So yes, so I present you the radial drift barrier as one of the main problems of planet formation, and that we couldn't explain before how to keep millimeter grains in the outer part of the disk. And one way to overcome this problem is to have multiple pressure bumps in the disk. And in this case, we predict rings and gaps around the star, as we observe today, and to basically know what is the physical processes that are doing this in the disk. I show you transitional disk as excellent laboratories to study this, and that we can have planet or dead zones. I didn't talk about the snow lines, but snow lines can also create rings and gaps in disk, and there is another way to distinguish between these two. And we can distinguish thanks to the comparison between scattered light and millimeter observations. And with that, I want to thank you for your attention.
Maybe do one or two questions before heading upstairs for cookies and more discussion.
So there is one system in EBS 7 would have this directed. How does it fit in this plot of like dust here?
Interesting question. Is the only disk where we have the evidence of a planet so far, and the mass is around 5 Jupiter mass planets. The segregation is large, so it's also like 20 AU in distance between the cavity size, or even more. So it looks like 5 is just like in the limit to explain that difference. Maybe we need a more massive planet or more planets than only one. Yeah.
How often, if at all, do you see full-time disks where all the stuff has gone the outer, anti-transitional disk, where all the stuff has gone the outer parts, outside, say, 30 AU, and you only have particles
in the inner disk?
in the inner disk?
Yes. We do. Actually, it's about to come. It's part of this, let me go. Let's go here. So in this sample of disk, this is from Taurus. All of these disks, actually, in this case, in the D-chart sample, they are mix of different star-forming regions, ages, and etc. This case is only Taurus. We are showing here only the disks with the structures, but in total, we observed 32 disks. Around 30% of them show structures. The other ones, the ones that don't show structures, are very compact. So we are concluding that what keeps the disk to be extended is the presence of pressure bumps. And the ones, because it's the same resolution and everything.
Very compact, but upper bands.
So the typical outer edge is, yeah, these are the ones with the structure. So the typical sizes are between 10 to 30 AU. Yeah.
You do solve them and they're about
Yeah.
20 AU.
Yeah.
And there's no boundaries around them.
No. In most of, so in Taurus, we also have the, I exactly don't know how many are binaries. They are well separated binaries. So we are seeing that they are also compact. But what it really changed there is the sharpness of the outer edge. So the ones that are binaries have a much sharper outer edge. Yes.
Is there any difference in the UV emission or accretion to extend this stars?
This is to be investigated. It's part of the paper, yes. We don't see it so far, a correlation between accretion rate and the presence of structures. Yeah.
Okay, well, let's thank Paola again. We can keep discussing this